Okay, so what I want to do today is I want to talk a little bit about some of the delicate convergence issues in Fourier series. And so I'm going to talk a little bit about some of the general theory behind it. Then I'm going to do some numerical examples written in Mathematica. There's other programs you can use. How many of you have used Mathematica to do calculations? One of the first things you should do whenever you use a computer package is check the normalizations. Mathematica does not normalize the Fourier transform the way mathematicians often normalize the Fourier transform. So you have two options. One is to read the documentation and see how it normalizes, and then just put in constant scaling factors. Or two, just hardwire the definition of the Fourier transform into it and just ignore the predefined function. And for some things, it's just easier to do it that way. All right, so what I want to do now is I want to talk a little bit about LP spaces. So LP of S is the set of all functions f from, say, S to C, such that the integral of the absolute value of f to the p power dx x in S is less than infinity. Okay, so these are the LP spaces. Anybody have any thoughts as to what would be good values of P to look at? What would be a good, interesting choice of P? No P value is interesting. This is bad. Come on. Somebody give me a value of P that might be interesting. Yes. 1. P equals 1. So for P equals 1 and F positive, you have probabilities. And a lot of analysis textbooks have what's called a dictionary between probability speak and analysis speak. And so if P equals 1 and your function is non-negative, things are wonderful. Any other good choices of P? 2. The other really good one is 2. P equals 2 is also good. Why is P equals 2 good? So what's so nice about P equals 2? You get rid of the absolute value if it's real valued. Absolute value of f squared is f squared if f is from S to R. So that's an enormous plus.
It's like the inner product with itself also.
Then you also have an inner product. And so, if f and g are an L2 of S, so is f times g. And that's extremely useful. So if you start in the space, a very simple combination will keep you in the space. So what's the key step in the proof that if f and g are in L2, then their product is in L2? It's one of the most famous inequalities in all mathematics. Koshi Schwartz. So Koshi Schwartz, I always forget, is there a T in this one? One of them has the T, one of them doesn't. I think Koshi Schwartz has the T, and then later the Schwartz space doesn't. I always forget which way it goes. So I'll put a little question mark. So what this says is if FG are in L2, then the integral of FG is less than or equal to the integral of f squared to the 1/2 integral of g squared to the 1/2, where I'm integrating over my space. So I'll put an s over here. This is a little cumbersome notation, so we often use f sub p to mean the integral of f to the p dx. And I think we take it to the 1 over pth power. And if you just think in terms of units, it's good to take it to the 1 over pth power. And this is just a more concise way of writing what's going on here. All right, so before proving the Cauchy-Schwarz inequality, I thought it might be worthwhile to investigate some choices of S. And you'll get a sense of which functions are in these spaces. So anybody have a good choice for S? What's a good choice of a set to look at? R. And what's the other good choice?
0, 1.
0, 1. So these two spaces will look very different. So what does it mean if I'm in L2 of R, or LP of R? Well, I've got to have good decay at infinity. So this requires good decay at infinity. What about just on 0, 1? Function's bounded. Could you do better than bounded? Does it have to be bounded? No. So things can blow up. Things can blow up in both spaces. But you don't have to worry about the space being infinite. So no issue from space being infinite. So here's the most basic question you could ask. I have LP of R, and I have LP of 0, 1, and let's assume P is greater than or equal to 1. What's the relationship between these spaces? So I've got here all the functions whose the integral of their pth power over R is finite. I have all the functions here whose integral of their pth power on 0, 1 is finite. Is it reasonable to compare the two spaces? Yes or no? Got to be a little careful. I see at least one person kind of squeaming. Why are you kind of squeaming?
Because you have to define the function.
Excellent. Here the functions are only defined on 0, 1. Here the functions are defined on R. Let's do the obvious thing by saying if we have a function defined on 0, 1, if we want to view it as a function defined on R, set it to be 0 everywhere else. And if we do that, what's the relationship between these two spaces? Is there a nice relationship between them? So what's the relationship between them?
It's not a subset of the one.
Okay, which one is the subset?
The one on the left.
Okay, this is a subset of this one. Why is that true? So here, you've got to be a little careful as to what do we mean by the spaces. Because here I could have a function that's defined outside of 0, 1. So maybe I have a function that's defined like this. If I now try to consider it on 0, 1, am I just looking at the restriction? If I'm looking just at the restriction, if I integrate to a finite number over all of minus infinity to infinity, I'll integrate to a finite number over 0, 1. So if you look at it with restrictions, that would be true. But you've got to be careful. You've got to somehow restrict the functions, because these ones are not naturally defined just on 0, 1. What if we go in the other direction? What if we take a function which integrates to a finite value over 0, 1, and we define it to be 0 elsewhere? Does it integrate to a finite value over everything? Yeah. So this is a very natural inclusion. If you think about it, I'm enlarging the space where it lives. So I'm allowing my function to have greater flexibility in terms of what I can look at. It makes sense that I can get new functions, that this is not going to be the entire space. This is really not the interesting problem to look at. I'm kind of tired, so I started with this, but this is really not the interesting one to look at. Why is this not so interesting?
P is the same.
I wouldn't say it's P is the same. It's the other. I'd go the other way. It's the targets, the input space is different. I'm often looking at a specific problem. I'm looking at functions on the unit interval, functions on a compact set. And I'm comparing functions that live in two different places. What's frequently more interesting is to compare two different values of P. So for example, LP of 0, 1 and, well, let's do L1 of 0, 1 and L2 of 0, 1. And let's do L1 of the real line and L2 of the real line. There's a fundamental difference between the two examples. What's the big difference between these two examples? between these two different target spaces, these two different input spaces? Any thoughts? The analysis in one is a little bit more delicate than the analysis in another. Which one do you think the analysis is going to be harder? R. Why R? And as a Bostonian, I agree that this is the much harder one to deal with. But usually you do not have a Bostonian lecturing in the subject. Why is this one harder? I'm sorry, it's infinite. So you have to deal with an infinity here. This one is easier because you're on a finite compact set. And so the analysis is significantly more tractable here than here. So the question is, what do these spaces look like? And a huge issue in convergence and analysis is what kind of decay does your functions have? And that's going to affect everything. So let's think a little bit about what these spaces look like. Over here, if you square a function, does it get larger or smaller? What do you think? Smaller. So 3 squared is less than 3.
Because it has to be less than 1 like most of the time.
Okay, it has to be less than 1 most of the time. Okay, so I'm going to assume everybody can remember the statement of the Cauchy-Schwarz inequality, and I will erase that for now and write a, let's see, oh, did it already die? All right. No, now it's working. Okay. Let's look at the following question. Question. Does there exist an f such that f is in L1 of R, L2 of R, dot, 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 L388 of R, but not L of 389 of R. Okay. What is special about the number 389? It's our class number, right? What else could I have used today? 2014, I could have used 1701. When was Williams founded? 1792, something like that? Any number like this doesn't really matter. So what do you think? If the function is in L1 of R, L2 of R, it's got to be decaying. So if I take higher and higher powers, shouldn't I have more and more decay? And thus shouldn't such a function not exist? So what do you think? Does a function like this exist? In other words, if I'm in it for a couple of L's, a couple of P's, then I'm in it for all P's from that point onward. That would be a wonderful condition. If you want to see if you're in L389 of R, just see if you're in LP of R for some smaller P. What do you think? How many people think such a function does not exist? How many people think such a function exists? All right, any thoughts as to how we might find such a function other than putting out an ad? How could we find such a function? So we want to find something that diverges. So what I'm going to do is I'm going to break the interval up into, say, things around the integer n. So here's the answer. So here's n minus 1, here's n plus 1. And what I'm going to do is I'm going to try to study the function near each integer n. So if I want things to diverge, I need a series that diverges. Anybody know a series that diverges? Harmonic. Anything else? No, good. All right. That is the quintessential go-to example. When you need something that diverges, think the harmonic series. So I need to choose a window length about this. And I need to choose a height. So I'm going to make triangles. And the triangles will get larger And maybe it'll get more narrow as I go further and further down. So I want the integral under this to be 1 over n when I take my function to be raised to the 389th power. Any thoughts as to how wide it should be? And how high it should be? So I want to get a 1 over n for the area. And I'm going to raise something to the nth power. So if I want the area under this to be 1 over n, how high should it go, and how wide should it be? So let's do it slowly. I should have maybe a width 1 over nb. Maybe I'll put in a 2 there. So it's on each side because I've got a triangle. I want my function to be continuous just because I want to impress you. Okay? I don't have to do it with this. I could do it with Gaussians. I could make it infinitely differentiable. I think a triangle's fine. I could have done rectangles as well. How high should it be? If the width is 2 over n to the b, how high should it be? N to the... so let's do n to the b minus 1 divided by what? Not 2. Well, when we raise it to the 389th power, things should go wrong. So if you want, initially, you could choose this to be n to the a, and then try to figure out what values of a and b do I want, such that when I raise this to the 389, things go haywire. And so this leads to the condition we want 389a minus b to equal 1. What's a good choice for a? You have an equation with 2 unknowns. You're going to have infinitely many solutions or none. What's a good choice for a? Simplest is a equals 0. I know, ZG, you have the right answer, but let's do a equals 0. What's bad about choosing a equals 0? So if I choose a equals 0, then as long as I choose b to be less than 1, it's going to blow up. But all of these functions will be the same. When I raise them to different powers, I'm not going to see any difference if a equals 0. Right? So why not choose a different value for a? The next easiest value to choose for a is 1. And so if I choose a equals 1, I then get b equals 390. And now I would get, and since this is a triangle, I have to put a 1/2 there. I get a contribution of n to the 389 over n to the 390, which is 1 over n. The sum diverges. And not only does the sum diverge, but if I looked at any smaller value, if I looked at the 388th power, 387th, 386th, I would have enough of a value of b that it would converge. So unfortunately, this example tells you that the behavior of functions at infinity that are integrable is not as you would like it to be. If I tell you a function integrates, you expect decay at infinity. That's not an unreasonable thing to expect. Do we have decay at infinity? Mostly. If you think about it, what is the set of values where the function is larger than any fixed amount? As you go off to infinity, that's getting smaller and smaller and smaller, because the windows here are shrinking as we go further and further down. The window is of size 1 over n to the 390. So as n gets very, very large, the window about each integer is getting smaller and smaller and smaller and smaller. Yes?
So does that mean to be yes after the question?
Oh.
Yeah.
Oh, sorry. I'm sorry. The way I thought I phrased it the other way around. Sorry. Yes. Sorry. There does exist such a function. Yes. Sorry. So unfortunately, the windows where the function gets large are getting very, very small. but there's infinitely many of them. So the set where wild behavior happens is very controllable, but it leads to enormous contributions. We'll see things like this when we get to the circle method, about very small subintervals where wild behavior happens can actually control what happens. So this tells us that just because the function is integrable, we cannot expect decay everywhere in the limit. What was a crucial fact for this? We had things going off to infinity. Could you come up with a similar counterexample if you restricted the function to 0, 1? So that's a nice example, that's a nice question for you to play with. Can I come up with a function on 0, 1 such that the integral of f is finite, but the integral of f, maybe f squared, f cubed, f to the fourth, but eventually f to the 389 becomes infinite? Okay, so try to think about something like that. Is that doable as well? But hopefully this gives you a sense of how difficult analysis can be, that your intuitions as to what functions look like are wrong. Okay, so now that we have this, let's prove the Cauchy-Schwarz inequality. Has everybody done copying this? Okay. So there's lots of different proofs of the Cauchy-Schwarz inequality. I think I chose to give the proof in the book because I wrote the book, so I must have liked that proof at one point in my life, and it's one of the most unnatural proofs there is. All right. So proof of Cauchy-Schwarz inequality. We use x in R implies x squared is greater than or equal to 0. This is considered by many to be one of the most useful inequalities in all of mathematics. Okay? So now the question is, how do we use something like this? Without loss of generality, let's assume f and g are non-negative. If you think back to the Cauchy inequality, we're trying to show the integral of the absolute value of f times g. Well, I can replace f with absolute value of f. I can replace g with absolute value of g. So if I can do it for non-negative functions, we can do it in general. Okay? So this is no real danger in doing something like this. Okay. So now let's let h of x, well, actually let's call it h sub lambda of x, will be f of x minus lambda g of x. And this is going to be real valued. So real if lambda is in R. So I want the subscript lambda to remind myself that this is a function not just of my f and g, but of some value lambda. And I claim 0 is less than or equal to the integral of h lambda of x squared dx. And we'll just integrate over our set S. So why is that true? That's just our inequality that if x is a real number, x squared is non-negative. So h is always a real number, so h squared is non-negative. So when I integrate this, it's got to be at least 0. So when I expand this out, this becomes the integral over s of f of x squared plus the integral over s of, I'll pull out the lambda squared, g of x squared, minus 2 lambda integral over s of f of x, g of x. And so if we pull this over to the other side, we get the integral over s of f of x, g of x is less than or equal to the integral over s of f of x squared plus lambda squared integral over s g of x squared divided by lambda, or 2 lambda, I guess. And of course, this is going to be greater than or equal to 0. Have I done anything wrong here? Or is there anything I have to be careful about? What do I have to be careful about in going from this line to this line?
Lambda can't be negative.
Excellent. So here, I need lambda to be greater than 0. If lambda were negative, I would switch the inequality. All right, so now we have something like this. And the question becomes, what's the smallest value this can become? Or is there a clever choice of lambda I can take? Right? So we have lots of different choices. I've got the integral of f squared. I'm dividing by lambda. What am I trying to compare this to? I'm trying to compare it to the integral of f squared times the integral of g squared. What would be a natural thing to take for 1 over lambda? Hope I haven't done this wrong. So the Cauchy-Schwarz was the integral of fg is less than or equal to the integral of f squared to the 1/2 integral of g squared to the 1/2. Look at what we have here. We have exactly what we want over here. We have the integral of fg. We have the integral of f squared over 2 lambda, and the integral of lambda over 2 times g squared. I want to try to choose lambda so that these terms look like what I'm trying to get over here. What would be a good choice of lambda? So I want to make the integral of f squared over lambda look like this, like the integral of f squared to the 1/2, integral of g squared to the 1/2. What would be a good choice of lambda? So, again, I don't want to just warp through the proofs. I really want to go through the proofs slowly and try to give you a sense of how you should think about them. So we have integral of f squared over lambda, and we want integral of f squared to the 1/2 integral of g squared to the 1/2. This is high school algebra. What should lambda be? So I want integral of f squared to the 1/2 integral of g squared to the -1/2. And now when I plug that in, the integral of f squared to the 1/2 makes this an integral of f squared to the 1/2. This comes up top. When I look at the other term, I have a lambda, so I'm going to end up getting this yield 0 less than equal to the integral over s of fg is less than equal to the 2's cancel, and I'll get the integral of f squared to the 1/2 integral of g squared to the 1/2. And note, lambda is greater than or equal to 0. So we didn't divide by -1. If we had divided by -1, that would have been horrible. Is there anything else we have to worry about? Damn it, we have to worry about lambda equals 0. What would it mean if lambda equals 0? What would it mean if lambda equals 0? Look at the definition of lambda. What's the only way lambda can equal 0? Or only ways? Maybe there's more than one way. Yes?
Either f or g is identically 0.
No, you're half right. So the comment was either f is identically 0 or g is identically 0. There's an asymmetry in how f and g appear. One occurs with positive exponent 1/2, one occurs with negative exponent, -1/2. So if the integral of f squared is 0, then lambda will be 0. There's another way lambda could be 0. What's the other way lambda could be 0?
G is infinite.
G is infinite. So handle the integral of f squared equals 0, integral of g squared equals infinity. All right, these are not difficult cases to handle. What would it mean if the integral of f squared is 0? Well, f's got to be basically 0 everywhere, because if f was positive on a set with measure, the integral of f would be greater than 0. And then when you look at the integral of f times g, if f is identically 0, or 0 almost everywhere, this side is going to be 0. The inequality trivially holds. Similarly, if the integral of g squared is infinite, great, the right-hand side will be infinite unless the integral of f squared is 0. So this is frequently what happens in analysis proofs. You know, you're making some kind of argument, and then at the very end, you've got to be a little bit careful as to how do things, you know, how does the argument finish up. And so over here, we're left with some special cases we need to look at. If you were writing this proof up nicely, how would you write it up? Would you write it up in this stream of consciousness that we did? I prefer teaching like this because I think this is more natural. But how would you write up the proof? How would you rearrange the calculation? So I would probably say case 1, integral of f squared is 0. Case 2, integral of g squared is infinity. Case 3, the integral of f squared and the integral of g squared are finite non-zero numbers. And then argue along these lines. So now we have the Cauchy-Schwarz inequality. So this is one of the most important inequalities in all of mathematics. And it's really just a consequence of the fact that the integral of, if x is real, x squared is positive. Okay, there's other ways to prove this. You could consider this a quadratic in lambda and ask what value of lambda minimizes the quadratic. You know, if you look at the top 10 ways of proving Cauchy-Schwarz, that's one of the strong candidates for top proof. And then you can see, well, what value of lambda minimizes this quadratic? Because the quadratic is not complex valued, the discriminant has to be non-negative, and that gives you a lot of information. Okay, so there's lots of different ways you can do this. I like this approach of being divinely inspired and choosing the right lambda, because if you have some idea of what you're trying to prove, you can sniff out what's a good choice. And here, when we're trying to get an integral of f squared to the 1/2, integral of g squared to 1/2, this makes a really good choice. Okay, I think this is almost all I want to say. Okay, so the only thing I want to say remaining about LP spaces is to go back to our original problem of inclusions. Where does L1 of 0, 1 live relative to L2 of 0, 1? So one of the real questions is, what does it mean for a function to be in L1 or L2? So structure of L1 of 0, 1 and L2 of 0, 1. So I need good functions to play with on 0, 1. What's a good function to play with? I want a function. I want to see if it's in L1 or L2. This is a fine time to be a smartass. Come on, give me a function. I'm sorry? All right, f equals 0, sure, it's in both. Give me a better function. Better function. X. Or more generally, any continuous function is going to be in both. Because a continuous function on a closed bounded set attains its maximum and minimum. It's bounded. So any continuous function is fine. So if I want to see anything, I need to find a function that is not continuous, or a function that's unbounded. Can you give me a good example of an unbounded function on 0, 1? 1 over x. We really don't have that many other choices, right? Instead of 1 over x, we could be a little bit better and do 1 over x squared. Okay, or more generally, 1 over x to the n, but n has connotations. P, R, well, we can't do P. Okay, P is wrong. P has been taken. We're talking about LP spaces. So we can do x to the r. So consider f of x equals x to the negative r, r greater than 0. I like to write it like this just so I know what's positive and negative. I don't like to have negative exponents, negative constants. It just bothers me. This way, my constants are always positive. So now if I integrate from 0 to 1 of x to the negative r dx, well, what's the danger value? The danger value is
0.
not 0, 1. Because if I have 1 over x, I have to remember this is the natural log. So I would get natural log of x at 1 and 0, which is infinity, if r equals 1. And then I would get x to the 1 minus r over 1 minus r at 0 and 1 if r does not equal 1. But more generally, we could integrate from 0 to 1 of x to the negative pr dx. And then the question would become, is pr equal to 1 or not? And so now we would get, it's going to be infinity if pr equals 1. And otherwise, it'll be x to the 1 minus pr over 1 minus pr at 0 and 1 if pr does not equal 1. So the cases that really matter is pr greater than 1 or is pr less than 1? If pr is greater than 1, I have an exponent here that's negative. And when I plug in 0, it's going to blow up. This will be a negative number. Negative times negative is positive. So it blows up if p times r is greater than 1, finite if pr is less than 1. So if you want an explicit example, if I take x to the negative 1/2 or x to the negative 3/4, these functions are in L1 but not in L2. So f of x equals x to the minus 1/2 or x to the minus 3/4. It's in L1 of 0, 1, but not L2 of 0, 1. So which space has the chance of being larger, L1 of 0, 1 or L2 of 0, 1? L1. So L1 of 0, 1 has a chance to be bigger. Because we just showed, here's an example of a function that's in L1 of 0, 1, but not in L2 of 0, 1. And in fact, that's true. So theorem, L1 of 0, 1 contains L2 of 0, 1. And the proof is actually one line. If f is in L2 of 0, 1, then the integral of absolute value of f from 0 to 1 is the integral from 0 to 1 of the absolute value of f of x times the absolute value of the function that's identically 1. And then by the Koshi Schwartz, that's less than the integral of f squared to the 1/2, the integral of 1 squared to the 1/2. And now the key fact here is that in the analysis, we have an interval that's finite length. And so because the interval has finite length, this is going to be a finite number. So here, finite length. Bless you. Okay? So for the Cauchy-Schwarz inequality to be very useful, we wanted to multiply f by the function that's identically 1. And we're okay. Do you think this proof works on R? Do you think anything in L1 is in L2? Do you think anything in L2, if I square it, do you think it's got to be in L1? So let's look at the other case. So here we crucially use the fact that we had a finite interval. We cannot use this Cauchy-Schwarz argument. What about L2 of R and L1 of R? We just showed L2 of 0, 1 was contained in L1 of 0, 1. Is L2 of R contained? Can you give me a function whose square is integrable, but the function's not integrable? Yes?
1 over x, but something else around 0.
Good. So let's do 1 over 1 plus absolute value of x. Or just do 1 over absolute value of x if the absolute value of x is greater than or equal to 1. Something like that. And now if I square it, it's going to be decaying like 1 over x squared. It's going to be integrable. But if I look at it just, it's the integral of itself, it will blow up because it'll be the harmonic. So sadly, L2 of R is not a subset of L1 of R. So we can find functions that are square integrable on R but not integrable. We can find functions that are integrable but not square integrable. The analysis is a lot more complicated. All right, so let me do one last proof. Proof L2 of 0, 1 is contained in L1 of 0, 1. Okay. So do we agree that we've already proved this statement? Right? We've already proved that L2 of 0, 1 is contained in L1 of 0, 1. What was the key ingredient in the proof? 0, 1 is closed and finite, and then what were we able to use to hammer away? The Cauchy-Schwarz. So the Cauchy-Schwarz is a very important, very famous inequality. The question is, do we really need something that strong to prove this, or can we handle it more elementarily? And there's a great way to handle this. So the absolute value of f squared. I want to compare the absolute value of f squared to what? So I'm trying to show that if I'm in L1, then I'm in L2. Right? I want to show if in L1, then in L2. So what do I want to compare the absolute value of f squared to? Absolute value of f. Is that the case? Is the absolute value of f squared less than or equal to the absolute value of f? I'm sorry?
If the function is greater than or equal to 1.
So if the function is greater than or equal to 1,
Less.
right, other way around. So if the absolute value of f is less than or equal to 1, true. So okay if the absolute value of f is less than or equal to 1. Unfortunately, maybe the function is large in places. Right? So the question is, which way, how can we compare things? So if the absolute value of f is less than 1, if we square it, we make it much smaller. Maybe we want to compare it this way. So what if we try to compare it this way? What can we say here? So I want to compare the integral of f to the integral of f squared. So that if I'm in L2, then I'm in L1. So I want to compare the absolute value of f to the absolute value of f squared. So it's always, what's the direction for the comparison? What relationship do I have here between the integral of, between absolute value of f and absolute value of f squared? When do I have an inequality? What do I need for this inequality to hold?
F greater than equal to 1.
Okay, so we're okay if the absolute value of f is greater than or equal to 1. And this will actually tell us which way we want to go. Over here, the problem is, if the absolute value of f is less than 1, then we have an inequality the way we want. Great, but of course the problem is maybe the function is getting really large. So this inequality does not help us at all. For this one, the absolute value of f is less than or equal to the absolute value of f squared. That helps us when f is large. The problem is, if f is small, this has become smaller, and that could hurt us. What do I need to add to this side? So f is less than or equal to 1 if f is less than or equal to 1. So this is deep. If the absolute value of f is less than or equal to 1, then the absolute value of f is less than or equal to 1. All right, exercise. Now what we do is we combine these two. And so if we combine them, we get the following. The absolute value of f is less than or equal to 1 plus the absolute value of f squared for all x. And so now the integral of the absolute value of f is less than or equal to the integral of 1 plus the integral of f squared. If my interval were infinite, would this break down? Yes. Good. Right? I should not be able to prove that, I have this inclusion when my interval is infinite. Good. So now this is another way of handling it. It's very similar to what we did before. We're not directly using the Cauchy-Schwarz inequality. We're using a very clever idea of replacing a function we want to study with two other related functions. Okay, we now have all the tools we need to really hit Fourier analysis. So we're going to go warp speed through Fourier analysis on Wednesday and Friday. On Wednesday, we're going to do the different convergences. I will warn you, I know the author, or at least one of the authors of the textbook very well. They tried, or he tried, to slip something past you in one of the proofs of either Fayet's theorem or Dirichlet's theorem. It is correct as stated in the book, but there's a subtle calculation that is being glossed over. So try to find the calculation that's being hidden. And we'll discuss that in detail, and we'll discuss why we have so much better convergence for Fayet series than Fourier series. We'll then talk about Poisson summation, and then we'll be able to hit Benford's law in great detail. Okay.